Great. Thank you, Dr. Potala, and would like to thank the organizers for inviting me and for holding this meeting and for everybody that's attending. And I will now tell you about the James Webb Space Telescope. I'd like to thank Gary Melnick and David Leisowitz yesterday for giving good introductions to it. And let's see here. This is as Dr. Potala said, I am at NASA's Ames Research Center. Also, I am a co-investigator on two of the instruments on this telescope, both the mid-infrared instrument and the near-infrared camera and spectrograph. So this is a large project. It'll be the largest science observatory that NASA has ever flown in space. And it's also partnered with the European Space Agency and the Canadian Space Agency. There are many people working on it. Probably at its peak, there were probably close to 1,000 people working on it a few years ago. And I'd like to thank everybody that has contributed material for this talk, including the Space Telescope Science Institute, the James Webb Project at NASA Goddard Space Flight Center, and many others. So what I'd first like to do is tell you a little bit about the science of James Webb, and then I'll talk about the observatory and its science instruments and also opportunities. This is very good timing because proposals are now being accepted. If you want to use James Webb, proposals are being accepted over the next 11 days, and anybody in the world can apply. So James Webb Space Telescope is different from the Hubble Space Telescope and many other space observatories in that it works in the infrared. And you've heard both from Dr. Leisowitz and Dr. Melnick about some of the advantage of the infrared. This is just sort of showing where the infrared falls in the let's see here if I can get my little laser going here. I think I'll just get the mouse. So this should show, if you can you see my mouse moving here? I think I've enabled that.
Yes, yes, we can see.
Okay, so this shows where the, oops, was a little ambitious there on the mouse. The shows where the visible light spectrum is. So this is what the eye can see in the whole electromagnetic spectrum, all the way from gamma rays through radio waves. Ultraviolet is filtered out by the atmosphere. The sun does not have much in the way of X-rays, which is good. There are some high energy events in the universe that produce gamma rays and X-rays that are very harmful to light. The sun mostly produces its radiation here in the visible range, and our eyes have adapted. And then longer wavelengths are in the infrared, and then microwave and radio waves. So James Webb is going to be working here. And you've heard some about, again, the infrared from Dr. Leisowitz and Dr. Melnick. This sort of shows where the Hubble Space Telescope is working in its range. So from the ultraviolet out into what's called the near infrared, to wavelengths that are about 3 times longer than what the eye can see, or 2.5 times longer. And James Webb will go from visible lights, from sort of not as blue as the eye can see, but it'll go out into what's called the mid-infrared. Now, why do we want to look in the infrared? And this is an example. This is a picture of a Hubble Space Telescope image of the Eagle Nebula. This is also called Pillars of Creation. It's been around a lot. This was, I believe, taken with a wide field camera 2 or perhaps a ACS and in visible light. And then this is what it looks like in the infrared. This is a Hubble image taken in 2014. So you see that visible light shows a lot of the bright stars, but it also shows this dust here that's very obscure, that obscures what is going on inside. In these clouds of dust and gas where stars are forming. And you go into the infrared, you see there's some very bright stars here in the infrared that were just completely invisible in the visible image. So there's a whole hidden universe that's missing. Also, another key advantage of the infrared or feature is that It's will reveal light that has been redshifted. In the distant universe, we know that things are moving away from us at very high speeds, and due to the Doppler shift, it means that any visible light is shifted into the infrared. This is a picture of what Hubble visible light images of these candles, galaxies look like. And you see they're very faint here, and then the same objects in the infrared with Hubble, these are just in the near infrared, you see are much brighter. And that's just because they have no light in the visible because they're moving away from us so fast. This is another sort of example of infrared revealing stars that are behind dark clouds and in dark clouds. This is called an infrared dark cloud that you see in the visible, where there are no stars visible, and then you move to infrared wavelengths and you can see the objects there. So there are many advantages for the infrared, and it enables a lot of science. So I will go over some of that now. There are sort of 4 science themes that were used to develop the capabilities of James Webb, although James Webb will be very capable and people will use it for many things that haven't yet been imagined. So the first theme is first light and in the universe and the epoch of reionization. What were the first objects that lit up in the universe? Well, we should be able to see the first galaxies. So back the Big Bang, the whole universe was just a point of radiation, and then the universe expanded, and then the hydrogen atoms nuclei formed, hydrogen atoms recombined after about 300,000 years, and then the universe cooled off enough so that gravity could overtake thermal energy and start to condense mass. Stars formed, galaxies formed, until we get to the present day. So this is just the nutshell version of the history of the universe, and James Webb will be able to look back in time and see what the first galaxies were like at well under 1 billion years, so maybe a few hundred million years after the Big Bang. We'll be seeing the first galaxies that came together. This will help us understand dark matter, and it'll help us understand the structure of the universe and the first objects. Then we'll also be able to understand how these galaxies evolve. This is a simulated image showing what early galaxies may look like. This is the Hubble Space Telescope has taken some deep fields, and we will be able to see if we stare in regions, be able to see galaxies over a big range of time and be able to understand from their shapes sort of how they evolved, how star formation progresses in the galaxies, and how they are driven by outflows and events. The third theme is the birth of stars and planets. We know now that stars form in out of circumstellar disks in dark clouds. Also, the planets form in these disks. It was this is very recently confirmed. The idea has been around, you could argue, for even hundreds of years, starting with Laplace in the 1700s. But, and then modern theory was developed, particularly in the 1980s or so, but disks weren't really observationally confirmed, both by looking at their Keplerian rotation velocities and their structures until the 1990s. So we now understand that stars form in these disks, and in the infrared, we'll be able to penetrate these disks and understand more about the processes, more about the chemistry, like what Professor Melnick was saying with water. And then the fourth theme is studying planetary systems and the origins of life. So this is both studying things in our own solar system and studying extrasolar planetary systems. I'd like to show you this transit technique. For you probably familiar and have this technique has been used for finding most of the planets around other stars, where if things line up between us and a star, when the planet moves in front of that star, it's the light of that star dims very slightly. And so over a period of an hour or two, when the planet is moving in front of the star, we see less light from the star. And then when the planet is moving off the front of the star like it is now, the light from the star comes back up. Well, we can't separate out the planet and the starlight, but we can see the star dim. So this technique has been used to discover thousands of planets, and now James Webb will be able to follow up a lot of those discoveries and characterize what's in the atmospheres of those planets. This is one very intriguing system that's relatively nearby around an M dwarf. I think it's only about 12 parsecs away, the TRAPPIST-1 system, where it has 7 planets that are in a very highly resonant orbit, all about the size of the Earth. A number of these, like D and E, are about the temperature of the Earth, are potentially habitable, and James Webb will be able to characterize some of their atmospheres. And there are a number of programs already doing that. This plot shows the how much flux that the planets receive from the star. So right in the middle, this 1.0 value is about where Earth, this is where Earth is, and see these other planets are very similar in the amount of light that's received, the amount of energy on this axis, and also the density of the planet on this axis. So these are very good targets for characterization. We know what the atmospheres of terrestrial planets in our solar system, Mars, Earth, and Venus would look like, and we'll be able to do searches for these features with James Webb. So this is a big carbon monoxide feature here at 15 microns, and then ozone around 10 microns, for example. And we see the differences. And Earth has ozone, which is indicative of oxygen, and that means it's in some sort of chemical disequilibrium, and that's caused by life on Earth. So it may be possible to start to search for this on some planets. This is a plot showing what planets James Webb will be looking at just in only its first about half year of time. So about 1/2 of the first year has already been scheduled for people that contributed to the observatory. This is called guarantee time. This shows all of the planets. There are like 30 planets here, and the different colors represent the different wavelengths that they'll be observed in for characterizing their atmospheres. And this x-axis is their mass. So 1 here is the mass of Earth, and Earth is at about 300 Kelvin, so a true Earth would be here. Most of the planets we know are warmer and larger than the Earth, so that's what most will be characterized. But also, most of these planets are cooler than what has already been done with the Hubble Space Telescope and lower mass. So that is just a very quick overview of the science, and we'd like to talk a little bit about the observatory now. So it is indeed a space telescope. These different components are that it has a 6.5 meter diameter mirror, which is pretty large by ground standards. It's huge by space standards. There is this big sunshade here, and what the sunshade does is it allows the sun and the Earth to always be on this side, and allows the telescope to be in the shade so it can cool off. And that's important for infrared observations, because the heat of the telescope can produce a background that can make the observations less sensitive if the telescope is warm. The instruments are on the back of the telescopes, they're on the back side, and the solar panels and all communication to the Earth is going to be on the warm side of the sunshade. So this shows the relative size of the primary mirror, 6.5 meters on James Webb. The Hubble Space Telescope is 2.4 meters. It's also a single mirror. There are 18 mirrors making up the primary of James Webb, and the Spitzer Space Telescope is another very successful space observatory, was a little less than 1 meter in diameter. So, the amount of light goes as the square of diameter, so James Webb will be quite capable. All of the mirrors are actually made out of beryllium for lightweight. It's a very low element on the periodic table, 4, and much lighter than using aluminum or other elements. And they're coated with gold because gold has very good reflectivity and low emissivity in the infrared. This sort of shows one of the primary segments being made. Quite a detailed process. They're made. They were all made at warm temperatures, and then they were tested, coated, tested together at cold temperatures. So that was quite a bit of work. This shows the different segments of the primary mirror. There are 3 prescriptions. There's this inner ring, all has 1 prescription, and then and then the outer rings, depending on whether it was a corner, the B's or not, or the C's, had different prescriptions as well. So, I mean, all of this is made. You can see pictures of all the elements. Just a little comparison of a large ground-based telescope, the Keck Observatory, compared to James Webb. Keck is 10 meters in diameter. James Webb is 6.5. So Keck does have, so the area of this is about 3 times bigger of Keck. However, Keck only goes out to a few microns wavelength in infrared. It is much less sensitive. James Webb will go out to much longer wavelengths. And to give you an idea of the mass, the total mass of the whole James Webb Observatory, including the spacecraft, which with all the communications is only 6 tons. And just the rotating mass of Keck, doesn't include everything, is 270 tons. So this gives you some idea of just the massive different technologies to make something light enough to send it into space. And also, it's more expensive to send things into space. It'll probably cost about 10 times more per hour to operate James Webb. It's an expensive observatory, but it can observe pretty much all the time. When ground-based observatories have day and night issues, you can't observe during the day. So I'll just go through this quickly. This sort of just shows the cutaway of the sunshade with the observatory on the cool side. The sun and the earth are over here on the warm side. This shows an actual photograph of the sunshade. It has to fold up for launch. This is it totally unfolded. You can see there's a person in the middle. The telescope usually goes here. And it has these 5 separate layers to be able to provide the cooling and sort of the whole radiation management. It also allows for some redundancy in case some small micrometeorites get through. So it won't let a lot of warm radiation in. This is a picture of the completed telescope. This was taken several years ago at, I believe this is at Goddard's Space Flight Center. And during testing in 2016 and 2017, all the instruments were tested then. This is showing all the science instruments. They were bolted onto the back of the telescope there. And this is the whole observatory. Now, this is down in Southern California near Los Angeles in the US. This sort of pink area is the sunshade all folded up. And then you can see here, that's the main part of the mirror. There's some wings on the mirror that fold in. And this will all now fit into the shroud of the rocket to launch it into space. So in addition to needing a telescope and the sunshade and spacecraft, you need some science instruments. This shows the wavelength coverage that James Webb will provide. And so this is visible light down here, and this is near infrared. You can observe some of these wavelengths on the ground, but much less sensitively than in space. And this is the mid-infrared that is largely inaccessible from the ground, at least at high sensitivity. There's both cameras to take images with James Webb. There's this near-infrared camera, mid-infrared instrument, and another near-infrared instrument and a spectrograph, and also spectroscopic capabilities. So we'll demonstrate and show some of that. This is what the focal plane of the telescope looks like. This shows this is sort of obscured by the central hole in the mirror, and this is the field of the near-infrared camera. It's about 2.2 arc minutes by 2.2 arc minutes on a side, and there are 2 fields adjacent to each other. The mid-infrared instrument is over here. It's a little over 1 square arc minute, or a couple square arc minutes total. The near-infrared spectrograph is over here, and it has several different modes, so I'll talk about them, and the nearest instrument. This is a picture of the near-infrared camera. It's very highly redundant. There are 2 identical versions of it that see the fields right next to each other. That was in the this previous slide here. There are 2 modules in NIRCam. They are mounted back to back, and they see adjacent fields on the sky. This will also be used to actually phase up all the mirrors of the telescope, so it has to be very redundant. This is one of its detector arrays in the near-infrared. It has 10 of these Mercad telluride detector arrays that go out to, some go out to 2.5 microns and some go out to 5 microns. This is a US provided instrument with Marcia Ricci at the University of Arizona is the principal investigator. The near-infrared spectrograph was provided by the European Space Agency, and it provides a spectroscopy over from 0.6, which is sort of red in the visible light range, out to 5 microns wavelength at these different spectroscopic resolutions. And it has single slits that has an integral field unit. It will take a spectrum of every single point within a small area. And then it also has this multi-object spectroscopy. So over a field, you'll be able to select spectra of individual objects. And that's enabled by this micro shutter unit. So this is an electron micrograph showing these things are only about 100 microns in size, and they can be controlled to open up. So if you have an image here, you can decide whether you want to take a spectrum of any given object by opening one of these shutters, and then you get the spectrum over here shown on the side. The nearest instrument is slit the spectrograph and camera, and it will do slit the spectroscopy at low resolution, mostly for emission line studies in the early universe. There's also that's this wide field slit the spectroscopy mode. And then there's this single object slit the spectroscopy mode. It'll be very useful for characterizing the atmospheres of transiting planets, like showed earlier, and also an aperture mask interferometer for very high spatial resolution instruments. And it's provided by the Canadian Space Agency with René Doyon as the principal investigator. The mid-infrared instrument is a joint project between Europe and the United States. Actually, Europe did most of the work on this, I must say. The United States provided the coolers and the detectors. And it's a very versatile both camera and spectrograph from the 5 to 28 micron range. So just a few more slides here. This is showing what the observatory will look like in the fairing of the rocket. It'll be launched by an Ariane 5 from the European Space Agency spaceport in Kourou, French Guyana. This is just a cartoon image of, and you saw the actual observatory a few slides ago, how it'll fit into the fairing. It's getting very close to launch now. So right now, we are in, excuse me, 2020, November. Right now, it's already completed its final testing. We're going to make sure that it all works after its final test. We'll be deploying the sunshade and some aspects of the spacecraft and be checking it out, and then we'll put it all back together. And it will ship from California in early next year, probably in in the summer of next year, it looks like. And then we'll arrive in French Guyana and then launch in October of next year. And there's actually very little work left to do. It'll take about a month after it leaves Earth to go to its orbit. It's not orbiting Earth like Hubble is. Hubble's in a very close near-Earth orbit that also forces it to go through day-night. It's going to be a much more stable orbit at this Sun-Earth L2 Lagrangian point. It's about 1.6 million kilometers away, and it's about 3 or 4 times as far away as the moon. It's going to take about a month to get there. And there will be a 6-month commissioning period after launch. So as I said earlier, about half of the first year of observing time has already been allocated, but there's a call now for 6,000 hours of observations. And that's due, the proposals are due November 24th. There are many different types, small, medium, large. All countries are welcome to propose, and there is some time set aside, at least 15 times for European member states and 5% for Canadians. Observations are going to start in May of 2022. That's after 6 months of commissioning after launch. And here is the website for the proposal opportunities. And I'll end here with a slide showing where there's some more information on the web for both about the telescope, this documentation of the observatory, and you can see also images of it being built. So thank you, and I'm happy to take any questions.